Happy Science Week indeed, and I'm joined by Dr. Naomi Lavelle. Naomi, it's brilliant to have you here.
Thank you so much, MC. I'm delighted to be here.
Are you having a great Science Week so far?
Absolutely brilliant so far.
Brilliant. Well, we've got loads of questions sent in for you to answer, and just one question for me to answer. So I want to say thank you to Ashel from Tyrrellstown Educate Together National School, who wants to know, where was the first episode shot? Well, Ashel, it's actually shot here in Dublin in a studio called The Coop in Harold's Cross, but no chickens on site. Now, we've got loads of questions about animals today, Naomi.
Brilliant.
And the first one is all about frogs. They want to know, how do frogs hear?
How do frogs hear? Actually, that's a very good question because we don't see any of these ear pieces on frogs, do we?
No.
This is called our outer ear, and frogs don't have them. So how do they hear? They do have, if you look closely at a frog, you'd see sort of a round disc just behind their eye. And that's actually called their tympanum. And that is like an eardrum, basically. We have eardrums inside our ears that help us to hear. And frogs have them just on the side of the face, basically. So when there's a sound, these start to vibrate, and that sends signals up to the frog's brain, and the frog can tell what it's hearing.
Oh, very good.
But I'll tell you an amazing fact is that in some frogs, the tympanum, I'm having trouble over that one, tympanum is actually connected to their lungs. Can you imagine having your eardrum connected to your lungs?
Oh, so they can hear themselves breathe, maybe.
Maybe, yeah.
Oh, very good. Great question. Thank you so much. That was from 4th class in Greystones Community National School. And they've sent on a second question, another one about an animal. They want to know, when you milk a cow, does it hurt? Now, I'm from a farm myself, so I think I know the answer to this one, but I'll let you take it away.
You could probably answer this one, no problem. So, no, it doesn't hurt, does it?
No, it wouldn't. No.
Because if it did hurt, we'd know, because then the cow would produce less milk. And we'd see the yield go down, and we'd know that they were in discomfort. So luckily, doesn't hurt the cows at all.
That's right. And I mean, you can tell when a cow is happy, because my own dad tends to play the radio when he's milking the cows, and it seems to put the cows at ease and in a good mood, would you believe?
Yeah, actually, your father's like a scientist, because there is research showing that cows will actually yield more milk if you play them the right kind of music.
There you go.
Isn't he very clever?
Now, Dad, you're outstanding in your field, you might say. Very good. And we have another question from Liam in Galway, and he wants to know, how can birds fly and how do they stay in the air?
Oh, very good question, Liam. So birds and flight. Well, birds' bodies are adapted to flight, okay? They have some very clever things. Firstly, if you want to get up in the air and fly, you're going to be light, aren't you?
Yeah, I'm going to...
Yeah.
I just come straight back
You
down.
and I won't do it so well because we have big, heavy bones, for one thing. But birds' bodies have become adapted so that their bones are hollow. So that makes them a lot lighter already.
Yeah.
Okay? And then we have those big jaw bones and a nose and a mouth. They're pretty heavy. Okay, birds, clever birds, they've adapted, so they have a little beak, okay? Much, much lighter. So they've gotten rid of all the heavy stuff, and they make their bodies quite light, which helps. But I'll tell you, one of the most important things with regard to birds and flight is obviously their wings.
Of course.
So I have made a very high-tech wing here out of paper. And if you have a look at the shape there, see, MC, it's kind of curved on this side.
Yeah.
And it's tapered in and kind of more flat on this side.
Yes, I can see that.
Yeah. So we call that an airfoil shape, okay?
Okay.
And that shape is how birds' wings are shaped. And hopefully we'll be able to demonstrate that this aerofoil shape is very good to help things fly. Will we give it a go?
Absolutely.
Okay.
Let's do it.
Let's move our bird over here.
So here's one you prepared earlier.
Just so happens, very high tech again.
Very good.
So I have one of these airfoil wings attached on here. Okay.
Oh, yes.
But if we want flight, we're going to need some air and some wind.
Oh,
yeah. Okay.
Right.
I may not do it. I think we need, that's it. We need a little more power.
Okay, let's do it.
So when you're ready, turn on the power. Oh, wow, look at that. So you can see that it is lifting. Oh, see that? Lifting up into the air. Oh, you might get it all the way to the top.
Oh my goodness, look at that.
Amazing. Okay, so that is how the bird's wing helps it get into the air and stay there too. It's all about how the air moves over and around the wing. So one important part is that the air moves over the curved part here, and then, you know, the way it's sloped at the back, So it's shot down then. The air moves over and downwards. And when the air moves downwards, it actually creates a force that pushes upwards from underneath the wing, which is what you just demonstrated.
Brilliant.
So the shape of the wing, this aerofoil shape, and the movement of the air is what helps birds fly and get into the air and stay there.
One small question, but hopefully one big answer to follow. Could we live on the moon?
Could we live on the moon? Okay, well, could. I guess in the future, anything is possible, right?
That's right.
You could be flying like the birds in a little while.
Absolutely. Some fake wings, maybe. Off I go.
Okay, so if we were to live on the moon, there's a few things we'd have to fix or improve on.
Okay.
Because there's basically no atmosphere up there. And from our atmosphere here on Earth, we get oxygen, which we need for breathing.
We do.
And we also get protection from the harmful effect of the sun's light, the radiation. So you'd need to compensate for those two things for sure.
Maybe some SPF 200, maybe 250 maybe.
I think you'd really want to ramp it up a couple of thousand there.
Oh, wow, okay, there you go.
But there is research. Scientists are working on soil that is very similar to the soil on the moon.
Okay.
And they have found it does contain oxygen. So it's possible that they can extract that and maybe use it. Because you don't want to be sending everything up like tanks of oxygen and everything else. So there's potential there. They've also even been making bricks and blocks and things like that from soil that is similar to moon soil to see if they could build structures and they might help against the harmful effects of radiation or...
I could imagine it might be a bit dusty.
I know. Can you imagine trying to keep that place clean?
I mean...
Yeah, with your feather duster all the time.
I don't know about you watching from home, but when I was younger, we always used to joke that the moon looked like a giant ball of cheese. But can you confirm it's not actually made from cheese?
It's not actually made from cheese, I'm afraid not. No,
so no food source there.
Exactly. Oh, speaking of food, though, you would also need your food, obviously. And again, you don't want to have that repeatedly having to send that up from Earth. So you need to work out how to grow your food. Now, the soil has potential, okay? There's a fair few toxins in there, but scientists have worked out things they can add to remove the toxins. And now they're working on what nutrients are in that soil and what are the ones they need so that you could grow your own food.
Okay.
And there is actually some water on the moon. It's in ice form. So you'd have to investigate whether you could extract that and use it as water. So there's possibilities there, but I don't think we'd be leaping into it just yet.
So you could say, watch this space. Pun intended
good.
there, I'm going to admit that one. Now, next question. I really like this one because it just says sinuses, why? Straight to the point, scientific answers needed. Sinuses, why?
Exactly.
Why?
No messing around
No
there.
messing around.
Okay, so our sinuses are these sort of cavities or little caves or holes in our skull behind our areas of our face, like our cheeks and our nose. And you know what? Scientists aren't too sure what we actually use them for.
Really?
Yeah. So there's a few theories, obviously. We love our theories. So it could be that our sinuses help regulate the air that we breathe in, changing the moisture content and the temperature as needed. So say you're breathing in and the air is very cold. Yeah. The sinuses maybe add some heat to that to settle the body down. Or if you're breathing in very dry air, then the sinuses might add moisture.
Oh, okay. So a built-in filtration system.
Exactly. So that's one possibility, probably the main possibility. But it could be that our sinuses are involved in how we sound, how our voice sounds.
Okay.
A little bit of echoing going on there.
Yeah. So the bigger your sinuses, the more hollow your voice maybe?
That's possible, maybe deep booming voices.
Yeah, maybe.
And it could be that sinuses had a role to play for our ancestors.
Okay.
But maybe that role is gone now. But we never kind of got rid of them as we evolved.
Right.
So there's another possibility.
The appendix of the face, you might say.
The appendix of the face, exactly.
Now, we have a question in from Emma's Junior Infants in Lekela ETNS in Drogheda. And they'd like to know, why do animals have 4 legs, but humans have 2? But of course, some animals could have 6 legs or 8 legs, and depending on the time of the day, a flamingo may only have 1. They're standing on 1 leg half the time. So I'll let you answer that one, Naomi.
Okay, so Firstly, we are animals too, us humans. But if we changed the term of legs to limbs, then we might get an idea of why this is. So animals that walk on all four legs have four limbs, and they have adapted to walking on all their limbs. So we say they have four legs. And that's an advantage if they want to move, run fast, even climbing. That can help a lot. We humans have adapted to walk on just two of our limbs, our legs. That leaves us two limbs, our arms, free. So rather than walking on them, we can use them for carrying and creative things and crafting. So we get an advantage with that too. So it's probably more how you use your limbs rather than how many you walk on. So some walk on four and some like us walk on two.
There you go. Hope that answers your question, and a great answer. And we have another question in from Ella in County Cork. She wants to know, how do plants grow and why do some of them not survive? And we have some plants ready that might help
We
explain.
have some plants ready, exactly. So plants are amazing things, aren't they? So just like us, plants need food to grow. However, we need to eat to get our food. Plants are super. They can actually create and make their own food. It's a process called photosynthesis. And what they do is they combine carbon dioxide and water, and they use energy from the sun's light to convert that into food.
Okay, very
Pretty
good.
impressive, isn't it?
I mean, the way we eat seems really boring now compared to that.
It does, doesn't it? So how do they do this? Well, this process of photosynthesis tends to happen in the leaves, or the green parts of the plant. So they can easily take in the carbon dioxide from the air around them.
Okay.
But the water, that's a little bit trickier because the water is down in the soil. So they need to draw it in through their roots and then up through the stem to where it's needed to make their food.
It's like a lot of work for the plant.
It does indeed. And if you think about it, we're used to water flowing downwards, right? Not upwards.
That's right, yeah. Streams always flow downstream, not upstream.
Exactly. So plants use something called capillary action that allows them draw the water up the stem to get it to where it's needed.
Okay.
Just so happens that we have a nice, simple and colourful experiment to show capillary action in action.
Fantastic.
Okay, so I have a piece of kitchen paper or kitchen roll here. And you can see I have put some blocks of colour along the end here. I've used water-soluble markers to do this. So we have a nice rainbow effect on either side. Okay, MC, will you pop either side of this into my jars?
Of course.
Glasses of water. Are we ready?
Here we go.
Capillary action, here we go.
All right.
Now.
Oh, it's absorbing straight away.
Exactly. So if you can see there, see the way the colour's creeping up already?
Oh, wow.
So that is capillary action. It's the same thing that happens for our plants, how they draw up the water. So the colours, because we use water-soluble markers, they are actually moving with the water as it moves up and around the kitchen roll.
Amazing.
So now, to help capillary action, we have water molecules. They're very sticky. They love to stick together, right?
Okay.
So as the first water molecules creep up the fibres in the little pockets of the kitchen roll or the stem in the plant, then they stick to their buddies, the other water molecules behind them, and they pull them up. And then they stick to the ones behind them and pull them up. And that is how the water creeps up. And as you can see, we nearly have a full rainbow.
I was just about to say a full rainbow. That's amazing.
It's a lovely, colourful experiment, isn't it?
It really is, and you can see the colours swirling in the water. Like if we were to hypothetically pour some of that water, the colourful water, onto the plants, would that dye the leaves or anything?
Actually, just so happens that you could do that. If you colour the water, say you cut some flowers and leaves off a plant and you put them in water. If you added food colouring, then you can actually see the colour come up into the flowers and the leaves. And yes, you're right. You could do an experiment like that.
Oh my God, there you go. Now, even I learned something new, and I hope you learned something new as well. That is such a cool experiment, and it's a great way to actually visualise all these good words like photosynthesis and capillary action. And we have more questions for you, Naomi. We have one coming in asking, why do some songs make us happy and some songs make us sad?
Okay, well, that's a great question because we all love music, don't we? So we often get an emotional response from music, Some people actually have very strong responses to music. These people, research has shown the people that get goosebumps when they're listening to music tend to have really, really strong emotions to music. But we've all listened to happy and sad songs and felt happy and sad.
Of course.
It's all about chemicals that get released in your brain when you're listening to the music. So if you were listening to a happy song, then a chemical called dopamine can be released into the brain, and that makes you feel happy, cheered up and all buzzed up. But if you're listening to sad songs, then a chemical called prolactin may be released into the brain. That's much sort of more mellow, calm, creates that kind of effect. It can make you calm, it can make you kind of feel a little bit like you want to curl up and get all cozy, and it might make you feel a little bit sad too.
Okay.
Now, why does the music make us feel sad? Well, scientists think it's because of the chords of the music. So the brain actually, without us realizing, is predicting what's coming all the time, particularly with music. And that usually works pretty well. But sometimes there'll be a chord, an unexpected chord in a song we're listening to, and that throws the brain out and actually triggers this response. So we feel sad.
Oh, okay. So if you're hearing a minor chord versus a major chord, your brain just doesn't know what to expect. Sounds a lot like my second class piano teacher when I was playing the sheet music wrong and definitely made her sad, I'd say. Well, that's brilliant. Naomi, we also have a great question in from Dara in Dublin, and he wants to know, what is a chemical reaction?
Well, listen, I just got another question.
Oh.
Yes. So before we come to Dara's brilliant question, let me just give you this one. I think you're going to like this one.
Right.
So Rangashay from Tara Hill and Gorey would like to know if penguins have knees. What do you think?
I'm suddenly questioning everything I know about the Antarctic. They do tend to wobble.
They do wobble. They do have knees. They do, but they're invisible. Well, they're not.
Oh.
They're invisible to us. They're up there under all their folds of skin.
Okay.
So they do have knees, but they're not, because usually we just see their feet shuffling,
That's
their
right.
body and then their feet shuffling. But their knees are up where they should be, but they're just covered by the skin. So they do have knees. So that's a great question, isn't it?
So they're just shuffling for fun, really.
Do you know, it's like wearing a big dress, isn't it?
The ice just
Trying to move
so
the big
slippy,
dress.
they're afraid to use their knees.
Well, that makes sense.
That's a great question. Thanks so much for sending that in. And actually, just before we get to our final experiment, I'll just say hello to a few more of you who are watching from home. Second class in Waterford in Educate Together. We've got third and fourth class in Scoil Iad Naofa in Rahina in Limerick. And Miss O'Keefe's fifth class in Holy Family Senior School in Port Leash. Lovely Leash, of course, to end on. Now, Naomi, Dara is dying to know about chemical reactions.
Chemical reactions.
So take it away.
Yeah, it's a great one to finish with, actually, isn't
Absolutely.
it? Okay, so what is a chemical reaction? Well, probably the best way to describe it is to say that we can only call it a chemical reaction if the things that we start off with get completely changed in the reaction and end up being something totally different.
Okay.
So molecules are made up of atoms. And in a chemical reaction, the atoms of a molecule get rearranged to make another molecule, a different one, which is a lot of terminology, really, isn't it?
Yes, it is.
So how about if we think about the atoms as letters
Okay.
and the molecules as words?
Okay.
So if we imagined that you had some words made up of letters, and a chemical reaction is like mixing around all those letters to make new words.
It's like a scientific anagram, you might say.
Exactly.
Very good.
So now that we have an idea of what a chemical reaction is, let's have some fun with them.
Oh, yes, that's what we're here to do. It's
That's what
Science
we're
Week
here to
after
do.
all.
Okay, so we use chemical reactions all the time. They're going on around us everywhere, even inside our bodies, okay?
Okay.
So I have just 3 simple examples of things we might use chemical reactions for. Okay, so let's be safe.
Oh, of course.
Chemical reactions, let's put on our goggles.
Safety first, of course. All
Okay,
right.
so-
Secured, ready to go.
We are ready to go.
I'll let you take it away there.
Thank you. So we do use, chemical reactions to launch rockets up into space, don't we? We were talking about the moon earlier.
Of course.
Remember?
Yeah, there you go.
Okay, so obviously we're not going to launch any big rockets today, but I do have a
Might
mini
need to
one here.
make a hole in the roof
I know,
if we do.
yeah, I know. We might not be too popular if we did that. So let's give this a go. Okay, I have a mini rocket, and I am going to see if I can make a chemical reaction that'll shoot this up into the air. Let's step back.
Houston, are you on standby?
Can you see anything happening?
Oh, I can see it bubbling.
Oh, there's
Have
a
we
bit of
lift
bubbling.
off? Woo! Oh, there we go.
Indeed. There we go.
Amazing.
So a mini rocket. Okay, we used a chemical reaction to launch a rocket.
Brilliant.
Now, next, sometimes we use chemical reactions to find out more about different substances. So you can see here that I have 3 glasses with clear liquid. I know that I prepared them, one with water, one with vinegar, and one of them has baking soda dissolved in water.
Okay.
The problem is I've gotten a bit confused and I can't remember which one is which. So I know that vinegar is an acid. And I know when we dissolve baking soda in water, that is an alkali.
Okay.
I also happen to know that there's a chemical reaction with the juice of this stuff, a red cabbage.
Red cabbage, my granny's favourite.
Has it with the bacon.
With the bacon
Oh, you
and
can't beat it. So there is a chemical reaction with the juice of cabbage, like this, that should help us out here. Okay? We're looking for some colour changes in our chemical reaction.
Colour changes.
So, MC, would you pour some of the cabbage juice into each of our glasses?
Absolutely. Cheers. All right.
Don't know we'll be drinking this one.
Okay.
1,
2. Oh, look at that.
Oh.
Oh, wow. Look at that.
Okay, so I have a quiz for you. I happen to know that the chemical reaction of cabbage juice with an acid like vinegar will give you a pinky reddy colour. So which one do you think is the vinegar then?
What do we think at home? I think it has to be the red one here.
It does indeed.
Cool.
Okay, so we know that's the vinegar. Now, when you mix it with an alkali, we get sort of like a bluey greeny colour. Okay. So that's an easy one, isn't it?
That's the one in
so
the middle.
that must have been my bread soda in water. And then you can see this one is actually purple.
Yeah, it's kind of stayed the same colour.
It is exactly that. It has stayed the same colour. We didn't get any chemical reaction. So that must be the water, because water isn't an acid or an alkali. So we didn't get any chemical reaction, so it stayed the same.
That's cool. And, if you put a little bit more vinegar, a little less baking soda, could you get different shades of the colours that you see?
You can indeed. So if you were testing stronger or weaker acids, stronger or weaker bases, you'd get different colours, like a whole range. So the acids go sort of very pink and then up to red, and the alkali or the base go sort of blue down to green. Okay. So you can get a whole load of different shades.
You could make yourself half a rainbow with all the different colours.
You could test out some things like lemon juice or washing liquid, different things that you have around the house.
So it could be a great one to try at home and see what kind of chemical reaction you can get with your alkalines and bases. Brilliant stuff.
For sure.
Now,
for sure.
This one is making me a little nervous.
Okay, let's swap places again.
Okay, let's swap.
Okay, so this one, sometimes we do chemical reactions purely for fun.
Absolutely. That's what Science Week's all about.
Exactly. It is Science Week. I thought we might have a little bit of fun with this one here. So I am going to add my final chemical into my bottle here, and we'll see what happens. Think you're going to like this one?
Oh, wait, is there a name on this particular experiment?
There is. It's called elephant's toothpaste.
Elephant's toothpaste.
And I think you're going to find out why
Okay.
it got that name in a minute. Are you ready?
I'll take a big step
Big
back.
step back. Are we ready?
Ready. Three,
Okay.
two,
3, 2,
one.
1, go.
Oh my
Oh.
Oh my goodness.
What a mess.
Oh wow.
Look at that.
What a way to end the show. Elephant's toothpaste, indeed. Naomi, thank you so much for all the amazing work on the
Thank
show
you.
today. And I hope you had great fun listening to all the questions that were answered. We'll be back on Friday for our science party at 11:20, and I'll be joined by Phil Smith, Phil of Science, and the National Reptile Zoo, and more. Have a great rest of your day, and don't forget to brush your teeth. Thanks. We'll see you soon. Bye.